guys, Akhenaten here. So today I'm going to give you two proofs that the square root of 2 is irrational. The first proof is the conventional one, and the second proof is interesting not only because it is less well known, but it also generalizes very accessibly to a more general result. That is to say, to the proof of a more general result, namely that any non-square natural number is such that its square root is also irrational. That is to say, if a natural number is not the square of another natural number, it cannot be the square of a rational number either. So let's start with the conventional proof, and then we'll do the unconventional proof. Next, we'll look at how that easily generalizes without using any further properties of the natural numbers to the more general result I mentioned. And we'll also show that the first result doesn't quite do that. That is to say, you need a little more effort. So all right, so let's start with the conventional proof. We have, let us say, the square root of 2 is equal to a by b, and we're going to arrive at a contradiction later on. So if this is true, and of course b and a are natural numbers, so we get that 2b square is equal to a square, right? So if the square root of 2 is indeed a rational number, then we must have a natural number b such that 2 times the square of b is also the square of a natural number. So that's necessary condition. And so now what we're going to do is that we're going to assume that p is such that 2p square is equal to q square, and of course we're also assuming that p is smaller than any other natural number which also satisfies that property. So now let's just take a look at this, and let's see what this equation tells us. So 2p square is equal to q square. So q square is divisible by 2, so it's an even number. And so then what can we say about q? So suppose q was an odd number, say q is equal to 2m plus 1, then q square is equal to 2m plus 1 the whole square, which is equal to and of course if we take these two terms in a bracket, well, it's very clear that both terms are divisible by 4, so the whole is divisible by 4, so it's an even number plus 1, so you get an odd number. So if q is an odd number, then its square is also an odd number. So that means since q square is divisible by 2, because q square is equal to 2p square, that means that q is even. So q will actually be of the form q is equal to 2m. So what does this mean? So q square is equal to 4m square, which is equal to 2p square, meaning that 2m square is equal to p square. So now let's have a look at this. So we started with the number p, which has the property that 2p square is equal to q square, and we assume that it's the smallest number having that property, and then we get another number m, another natural number m, so the 2m square is equal to p square, and m of course must be less than p, because if m is greater than or equal to p, then this LHS, this left hand side, is at least 2p square, whereas the RHS is just p square. So m is definitely less than p, and m satisfies the property, this property that 2 times the square of m is another square. So we started out with a number which we said was the smallest number having a property, and we've exhibited a smaller number having the property, and this of course provides the necessary contradiction and gives us the proof. So this is the conventional proof that the square root of 2 is an irrational number, right? So so the next step, we will give you the I will give you the unconventional proof, and I will show you how we can generalize that to prove an even more general result. All right. So now let's dive into the second proof technique that we use to prove that the square root of 2 is irrational. So once again, the square root of 2 is equal to a by b. Let's assume that this is possible. So now, once again, even in the first proof, what we did was we identified a property of natural numbers, and then we showed that if a certain number has a property, then a lesser number must also have the property. And from that, we concluded that no numbers can have the property, because otherwise it would violate the condition that for any subset of natural numbers there must be a smallest natural number. So here, in the first case, the property we chose was 2 times the square of number. So our property was something like 2b square is equal to a square. That's if we have a natural number, so the 2 times the square of that natural number is also a square of a natural number. So that was the property we used in the first instance. Here we are going to use a different property, namely that b into the square root of 2 is equal to a, where b and a are both natural numbers. So b, a belong to n. So if we have a natural number b which has the property that b root 2 is equal to a, which is also a natural number, so that's the property that we're looking at here. So, but clearly if square root of 2 is equal to a by b, then b must have the property. So what we do is let p be such that p root 2 belongs to n, and p is assumed to be the smallest natural number which has a property. So now what we have to do is to find a smaller number p dash, assuming that p has this property, we find a small number p dash which also has this property, and our candidate for p dash will be p into square root of 2 minus 1. Right? So now you look at p into square root of 2 minus 1. First of all, look at this term in brackets, square root of 2 minus 1. So 1 square is 1, 2 square is 4. So the square root of 2 lies between 1 and 2. So square root of 2 minus 1 is a positive number, but it's also less than 1. One moment. What that means is that p into square root of 2 minus 1 is going to be less than p, and it's going to be greater than 0. So it's a positive number that is less than p, but also this is equal to p dash is equal to p root 2, let's put that in brackets, minus p. So p root 2 is a natural number, as by the definition of p, and p is another natural number. So it's the difference of 2 natural numbers which is greater than 0, which is positive. So that means that p dash is also a natural number. So, and then finally, let's look at the defining property of p. So does p dash also have this defining property, namely is p dash into the square root of 2 also a natural number? So that's what we're trying to find out, and indeed that's what we will find, because p into square root of 2 minus 1 into square root of 2 is equal to 2p minus square root of 2 into p. So once again, this is the difference of 2 natural numbers, and it's also positive, because have a look at this, p is positive, root 2 minus 1 is positive, root 2 is positive, so this whole number is positive. So this is a natural number. So we started with a number p, number that satisfies this property that p root 2 is a natural number. Then p dash must also satisfy that property. So p dash is equal to p into square root of 2 minus 1 must also satisfy the property. So once again, we get the required contradiction and we prove the theorem. So the difference with this method is that we can easily generalize this to a more general result, which says that one moment. So if the square root of n does not belong to n, then square root of n does not, if square root of n does not belong to n, then square root of n does not belong to q. So that is the result. That's the more general result. that we are going to prove next. All right, so now now that we know what result we have to prove, we do the exact same thing that we did in the square root of 2 case. So again, let the square root of n is equal to a by b. So now what we're going to do is again in this case, so b has the property that b into the square root of n is equal to a, where b and a are both natural numbers. So now what we're going to do is we're just going to introduce a little notation. So what we're going to do is we're going to talk about this square root of n. Actually, you can use any expression. So this is this kind of a bracket. So that represents what we call the floor function. So the floor function of any real number is the natural number to the left of it on the number line, and the floor of any natural number is the natural number itself. So if you have a real number that lies between two natural numbers, so what is the natural number that lies to the left of it on the number line? So the greatest natural number, which is less than it. And for any natural number, the floor function will just give you the same natural number. So the way it works is something like this. So you have 3.5. So the floor of this is 3, and the floor of 3 is also equal to 3. So for any natural number, the floor is equal to itself, whereas for any number that's not a natural number, the biggest natural number that is less than it, if a number is not a natural number, then it lies between two natural numbers. So what is the smaller of those two natural numbers? And that's what the floor function gives you. And of course, there's we're not going to be using that, but there is also something called the ceiling function, and the way that works is it gives the larger of the two numbers between which a real number lies. So the ceiling of 3.5, for example, is equal to 4. So we're not going to be using that. But anyway, what we know is that for any natural number, its floor and ceiling are the exact same natural number. Whereas for a real number that lies between two natural numbers, the floor is the lesser of the two numbers in between which it lies, and the ceiling is the larger of those two numbers. So for 3.5 on the number line lies between 3 and 4. So this is the floor, and this is the ceiling of 3.5. So that's how the thing works. That's how the notation works. So now what we're going to do is remember that we have chosen n to be a non-square. So what it means is that the square root of n is not a natural number, and so the floor of square root of n is equal to p is a natural number, and of course and p is not equal to the square root of n. So that follows from the fact that n is a non-square, and also the square root of n minus p will lie between 1 and 0, right? So because p lies, the square root of n lies between p and p plus 1, so this number lies between 0 and 1. So once again, so as in the previous case, so if the square root of n is equal to a by b, then b satisfies the property the b root n is equal to a. I think p for us, we already defined p as the floor of square root of n. So let r belong to n, and r root n belongs to n, and r is the smallest, assumed to be the smallest number with that property, right? So now what we try to do is once again we try to generate a smaller r, which also has this property, and of course that'll take the proof through. And of course our candidate, as usual, will be r dash, which is set as r into root n minus p, right? So r dash is set as r into root n minus p, and once again, since we already identified the square root of n minus p as lying between 0 and 1, so it's positive, so r into this is positive, and at the same time r into square root of n minus p is less than r, and this is greater than 0. So that's observation 1. Observation 2 is this is equal to r into the square root of n minus p is r root n minus p. So it's the difference of two natural numbers. R root n is of course a natural number, and p is a natural number, and it's the difference of two natural numbers, and it is positive. So it's also a natural number. And of course the final thing we need to do, the final thing we need to look at is that r dash into root n is equal to r into root n minus p into root n, and once again, all these factors are positive, so this whole number is positive, but also this is equal to nr minus r root n into p. So this term in the brackets is a natural number, so multiplied by natural number is another natural number. So you have these two natural numbers. It's a difference of two natural numbers, and it's positive, so it's once again it's a natural number. So in this way, once again, we generate starting from a number r, which satisfies the the basic property that r root n is a natural number. We get a smaller natural number, and of course, if r was already smaller, designated as smallest, defined as the smallest number of the set, well, we get a contradiction. So the exact proof technique without adding any further properties of natural numbers gives us this generalization. And now the next thing we'll try to do is we'll try to generalize the first proof in this way and see that it doesn't work. At least you need something else to make it work. All right. So that's the next step. All right. So now when we come to the last phase of this presentation, so what do we do there? So square root of n is equal to a by b. So in this case, we try to exploit the property that nb square is equal to a square, right? And so the next step should have been, let's say, if we could actually make this work, the next step would be something like if n divides a square, then n must divide a, right? Because in the square root of 2 case, what we were able to say is that if a square is an even number, so a must be an even number. So the generalization of that here would be that if a square can be divided by n, then a must be divided. You must be able to divide a by n. But of course, that's not true, and it's quite straightforward to show that. Straightforward to give a counter example. 36, for example, is is equal to 4 into 9. On the other hand, 6, 36 is of course 6 square, but 4 does not divide 6. So this clearly tells you that the method that is used in the first proof does not really generalize. I mean, you can still rescue it. You can use the things like the factorization of factorization properties of integers to make the proof go through, but not directly. So that's the advantage of the second proof. So that's a gain. Not only do we have an alternative proof technique, but we have a proof technique that that generalizes comfortably to give you a much broader result. So, well, thank you.